Well, hello, everybody. I'm really sorry that I was not able to be at the conference. I had a meeting in Nice, in France, that I really had to chair. But it's still nice to be able to report what we've done as our part of the demography project, and particularly in relation to environmental change. So you can see on the second slide the way in which the environment fit into the overall program of the demography piece of research. Our particular task was to look at two things: air pollution and climate impacts on heritage. And of course, much of this was going to be indoor heritage, so we had to be sensitive to the notion of how does air pollution get transferred indoor, how does climate get transferred indoors. Now, of course, over the last few decades, climate in the UK has changed enormously. And this next slide shows a map of the average temperature for the 30-year period centered on 1975, and the change up to the 30-year period centered on 1995. And what you can see is, particularly in southeast England, a dramatic increase in the average temperatures. Not unexpected, but part of this whole idea that we're seeing enhanced warming. Now, temperature is not always the most critical factor in heritage, and relative humidity can be equally, if not more, important. And so the next slide shows the vapor pressure of water and the changes in average vapor pressure across the same sort of period. What you see here is an increase in vapor pressure. Now, you might think, gosh, that means an increase in humidity. Well, in fact, it doesn't mean an increase in humidity because, of course, the temperature has increased in parallel with the vapor pressure, and in fact, the relative humidity reduces over this period. And we can see notable, again, the notable reductions can occur where the climate is warmest. So the following slide shows part of a project that we recently undertook where we looked at the humidity in the southeast of England, because while temperature records are readily available, long-term humidity records really aren't available over the same length of time. So there are two very good and lengthy sets of humidity measurements in the southeast, and both of these relate to Heathrow and Gatwick as two airports. So the Heathrow and Gatwick airport sites have run since the 40s and 50s. So we have very long records there. And if we look at those records, and these records are available from the MIDAS database, as shown in the next slide, what we can see is that over the years that we have records for, both at Gatwick and Heathrow, there's a gradual decrease in humidity. The relative humidity starting off in the early part of the record, in the 80s, and by the present period, it's down to the high 70s, a very substantial change. And of course, if you look at the predicted data for the future from the UK SIP output from '09, what you see is a continuing decline is projected into the future. So there will be slight changes in relative humidity projected into the future. This, of course, is outdoors. The summer, the drier conditions are particularly important in summer. And also, if you look at the second graph there, the lower of those graphs, what you can see is that essentially what we see is increasing humidity in terms of absolute humidity at night. So there's more water in the air, but nevertheless, the relative humidity in terms of a diurnal cycle doesn't change greatly. This kind of record presents us with some problem, though. Here in the next slide, I try and predict the salt transitions. How many damaging events will there be in terms of the crystallization of sodium chloride, an unhydrated salt that might cause salt weathering? Now, the MIDAS record, the observational record, suggests an increasing number of those salt transitions across the period from the 50s through to the current time. Now, that is due, of course, to the relative humidity becoming drier, and we've got more frequent transitions that cause crystallization of salt. However, if you try and predict these into the future, these daily moves from a position where there's high relative humidity on one day and low relative humidity on the next day, if you use the data from the UK SIP record, you would predict in the future a decline in the number of damaging cycles. And so that presented a kind of problem. However, this is an artifact of the predicted data. And if we look at the next little inset, what we can see is that the MIDAS data has a much narrower spread of changes in relative humidity than you predict UK data. We're able to correct for that, and we've published this in a recent paper. And these corrections essentially lead to the notion that what happens is, yes, the number of salt transitions increases throughout the late 20th century, but it then reaches a fairly stable value into and through the 21st century. But this warns us, of course, about the dangers of overreading the records provided from output of models like UK SIP. We have to be a little bit careful when you're really pushing these to the limit. But there's a case where we see increasing number of damaging salt transitions through the late 20th century and then rather leveling out through the 21st century. However, something in the next slide where there is a very dramatic increase throughout the future is the number of hot summer days. And here we see hot summer days of 25 and above throughout the number of those days throughout the next century. And what we see is, of course, they increase dramatically both at Heathrow and at Gatwick. And we can also see a slight change in the seasonality of the number of very hot days. So these change over time, and we get a different seasonality. And that, of course, could lead to different ways of managing properties, where the days when properties are open and are visited and the extent to which visitors use the indoors and the outdoors can vary depending on the climate. The next slide shows an attempt to try and transfer these outdoor measurements indoors. So here we see firstly the outdoor measurements made at Gatwick on a daily basis over many years. And we've applied, so then if you look at the next way, we've tried to predict what the indoor temperature would be on the basis of those outdoor measurements. And there's our predicted value using a simple transfer model developed by Paul Lancaster. And this model does fairly well. As you can see, the red overlay shows a very good agreement between the model predictions and the measured values indoors. So if we know outdoor climate, we can make a fair stab at indoor climate, provided it's been calibrated to a particular room. And that's, of course, what we've done in the next slide. Here what you see is, you see the outdoor temperature in the upper part of the graph, and then you see the indoor temperatures for 2 rooms where the model has been calibrated. And of course, they show the same increasing trend. The indoor temperatures are slightly higher than the outdoor temperatures because the building has some kind of solar gain. The bottom pane suggests that up until 2040, 2050, there's not really much different scenario in protection. They diverge after about the 2040s, but up to 20, the whole thing is fairly scenario independent. So these increases in temperature in terms of the strategic planning up to 2040 are model or scenario independent. So we have increasing temperatures indoors regardless. Of course, those are the annual averages. What you see in terms of the seasonal picture is just a little bit different. And this shows the current seasonal differences in temperature, and we see, of course, lower summer temperatures at the moment and higher summer temperatures in the future, and it converges a little bit in the winters, although in the winters, of course, the future is still somewhat warmer. So that's the position with temperature. If we look at relative humidity, We can see here the position with relative humidity. Outdoors, of course, relative humidity declines, as we've already discussed, because of the warmer temperatures and only a slight increase in the amount of water in the atmosphere. But what's interesting is because of all sorts of buffering processes, indoors, essentially, the predictions are that relative humidity won't change very much. So that looks like a very stable condition. However, that conceals one of the changes that's underway, because if we look at the next slide, what we see is that, of course, when you break it down into seasonal change, what happens is that, yes, the future summers are very dry, but the winters are just a small amount damper. So we might get slightly damper winters and very much drier summers indoors in the future. So a very important thing to see that the changes are spread throughout the year, and those changes take on a different sign if we consider seasonal changes rather than the averages. And what about air pollution? The next slide shows how we looked at air pollution at one of the sites that we were interested in for the demography project. And we see here that Broadsworth is very surrounding monitoring stations for air pollution. And we chose a group, Barnsley and High Muffles and at Broadsworth. For example, here we see ozone, we see the ozone concentrations throughout the year, and we see the ozone concentrations on a diurnal basis. And we see the April to September measurements. These were chosen because this is the opening season. And what you can see is a very clear spring maximum, particularly at the remote site up on High Muffles. The Barnsley site doesn't show that because the Barnsley site is in a city where, of course, there are many other reactions of the air pollutants with ozone. So it's likely that the High Muffles site most closely resembles the kind of experience that you would have at Broadsworth. Nitrogen dioxide is measured both at High Muffles and at Barnsley, and what we see here is the Barnsley site. Of course, nitrogen dioxide is a pollutant much higher in Barnsley than at High Muffles, and also you can see that the diurnal cycle in the urban setting is much more pronounced than at High Muffles, where being a rural site, it's flat through most of the day. So it's likely, of course, that Broadsworth would experience more the kind of conditions that are found at High Muffles. Sulfur dioxide, we have data from Barnsley and Scunthorpe, which we can use to predict the values at Broadsworth. And what we see here is we see strong diurnal cycles due to human activity. And of course, we see a seasonal cycle also showing peaks again in the spring. These spring peaks are often due to things such as different states of atmospheric stability. So what does that tell us then about pollutants at Broadsworth? So the first thing we've got is we've got just a few measurements, therefore, of we can predict something about the indoor-outdoor ratios because we have a limited number of measurements at Broadsworth. You can see here the NO2 measured indoors and outdoors, the SO2 measured indoors and outdoors, and the ozone measured indoors and outdoors. Notice that ozone has a higher concentration. The indoor-outdoor ratio at these things, you can see that the nitrogen dioxide and the sulfur dioxide have a modest indoor-outdoor ratio, so perhaps the indoor concentration is about half the outdoor concentration because the pollutants are deposited. But look at the ozone. The ozone is incredibly reduced. Hardly any ozone makes it indoors. Even when the ozone is high outdoors, indoors, the ozone is relatively low. That shows us that, of course, ozone is strongly absorbed on the indoor surfaces. And this is particularly significant. What we've done is we've tried to predict the changes into the future, and the next slide shows some predictions for the kind of changes in a marine site in red and a continental site in yellow. And what we see is that there is a potential where you have continental air of ozone increasing in the future. This is mostly due to increased photochemistry and also the higher evaporation of the hydrocarbons that generate the ozone through photochemical reactions. So we could expect in continental air, slightly higher ozone. But the point is shown from the work at Brodsworth is that fortunately ozone is one of those pollutants that tends to be reduced the most in indoor air because it's heavily deposited on the outdoor surfaces. So although the news might look somewhat bad with increasing ozones, it's probably the least pollutant that we worry about least. In terms of temperature and humidity, what we see is, yes, very much warmer interiors in the future, which may, of course, mean that insect growth or mole growth, perhaps in the warmer autumns, becomes more significant. But relative humidity changes only slightly on average, although the seasonal cycle makes slightly damper winters and very much drier summers. So that was the kind of contributions that we were making to the collection's demography project. Thank you.